quite popular these days, and they are readily available on all the websites these days, and they're pretty cheap also. So you have a human body module, you have a sound sensor, vibration sensor, clock module, raindrop sensor, temperature, humidity, and there are many other sensors. And these sensors, because of the availability of these sensors, you may play around them, you can buy them, and then having one particular controller board, maybe Arduino or Raspberry Pi or some other controller, Jetson Nano or something like that, and then you can try these sensors by your own, because they are pretty cheap these days and are available everywhere. These sensors are actually available in this form, very core form, very raw form. They provide you the data in a very raw form. But when they come in the form of like application or in terms of products, then your smartphone on the right hand side, you see that the smartphone is actually one of the popular application, or actually I would say the popular host for these different sensors. Because you have accelerometer, gyroscope, you have proximity sensor. So whenever the screen or the display comes near to any obstacle, for example, when you are in the call and you bring your phone towards your ear, the screen turns off, right? The display goes off automatically. It happens because of like there is a proximity sensor sitting on the top of your of the screen, right? So there are several other sensors that are being used in the games. And you have like several gesture, like you have when you flip the phone, your camera may turn or something like that. So you have several sensors in the smartphone. You have sensors in industrial automation, where you have several robotics arms. They are being used to manufacture the different items in the industry, and those sensors are being equipped, and the data is being analyzed in order to do this right production in the right manner. You have autonomous car consisting of several sensors these days. Like Tesla, you have several sensors, especially the camera sensors. They are sitting on like in the windshield, and there are many other sensors that are continuously observing the environment and taking the decision for that is helping to the driver, or even in the driverless cars also. You have a smartwatch in order to count your number of steps, in order to have track of your daily routine activities, health monitoring sensors you have there in order to monitoring your health, or like heart monitoring sensor is also there. You have SPO, which measures the oxygen in the blood flow and something like that. So you have several sensors around you that are being used for betterment or improving the lifestyle of the human. Now, given those sensors, like this sensor generate a lot amount of data, and that data is, you may call it a sensory data. So that sensory data is essentially doesn't do anything. You have to perform some kind of analytics on that data. Without the analytics, that data is just a data. Unless you are building some analytics on them, you build some kind of classification or some kind of clustering algorithm, some kind of machine learning algorithm. Without those algorithms, the data is just the data. It is not being useful. It is not useful. It is not itself doing anything. So we have to make some decision. And in order to make the decision, we have to build some algorithms on the data. So the data gives you the information that, okay, this phenomenon looks like this. And based on that, what decision you want to make, right? So those algorithms are important there. One of such algorithm you can consider as ILD classification. So if you look at this figure, so on the top of, so on the upside, I hope that you can see my cursor when I move my mouse. Can you see my cursor? Hey, Nilesh, can you see my cursor?
Yes, sir.
Yes, sir. Yes.
Okay, that's great. Because I just wanted to make sure, because I'm just hovering it around on the slide, and I just wanted to make sure. So you have this classification approach at first. And in general, a classification algorithm is a machine learning algorithm. You can consider as a deep learning algorithm also if you consider an underlying network model or neural network model. So you have this classification model, and this classification model, what it does, So what it does basically, it takes a training data set, and this training data set mostly contains several instances along with their labels. So the data set itself is labeled data set. So the instance in this particular case, I can consider as a time series, because the sensor generates a time sequential data, and that that one particular length of time series may be considered as a one instance, or you may call it like one sample. But within this time series, you have several data points generated by a particular sensor. So you have one instance and you have one label associated with that instance. So such instances are there for different class labels in the training data set, and you have several corresponding labels. So given this training data set, machine learning model or a classification model will try to learn some pattern out of it. And those patterns will be used whenever it comes to prediction, make a prediction on some new time series. So for example, this sensor is generating a time series, and when it gets completed, a classification approach will predict its class label because it has been trained on the training data set already. Now, there is a important meaning with this like complete word here. The complete I mean to say here is the number of data points that are required to predict its class label should be the same as we have trained in the training data set. So in the training data set, if you have like 120 data points in one particular time series, then the sensor needs to generate 120 data points in order to predict its class label. On the other hand, if you go for early classification, you don't have to do that. You don't have to wait till the end of the time series. So you may have like an incomplete time series, and so the sensor is continuously generating the data, and even it is not completed, it is not reached to like 120 data points. It is like, let's say, 90 data points as of now, and with those 90 data points, early classification model will be able to predict its class label. The one thing is to notice here is the training data set. The training data set would be same in both the cases. So you have classification and you have early classification. They both take same data set. So training data set would be the same. However, this change you will notice only during the testing time. So testing time, because the training most of the time it is being done offline, and once the model is trained, it is being deployed for the real-time purpose. In real-time purpose, you will not wait for 120 data points. Although you have, let's say, these 120 data points you may be generating in just 2 seconds. But like if you can make the decision even less than in 2 seconds, then it will improve the user experience. For example, if I take the example of this, like turning on the camera by flipping or performing a gesture on your phone, then you just do it like in a second, or maybe in 2 seconds. So the faster the algorithm is able to classify that you are making to move, you are going to make this gesture, then it will turn on the camera. So it will improve the user experience as soon as it turns on the camera. What happens if you just like flip your smartphone or actually hover it somewhere else and you're trying to open the app, let's say camera app, and it is taking some time. The time would not be that much. It will be like 1 second delay or maybe 2 second delay, but it will look, in terms of user experience, it will look bad. So the early classification there will be very helpful. So in such applications, you may consider that early classification is very helpful there when it comes to like sensory data, and you can save some of the data points while making the decision. If I go to extend this idea for multivariate time series, then you have bunch of sensors. You have multiple sensors here, and they are generating the time series. And that time series can be called as a multivariate time series. So again, the idea would be the same here. And instead of waiting till the completion of MTS, you may predict its class label with the incomplete one, right? And the amount of data that you saved, because that data needs some time to generate also. So that's why I'm calling it like earliness. So you achieve this much earliness, right? And this much earliness is required in order to like make prediction of its class label. So there are a couple of potential application of early classification. So the first application you can consider as yoga assistance. So if a person or actually a user is equipped with several sensors, for example, there are 4 different sensors or motion sensors on the 2 legs and the 2 arms, and these motion sensors are generating continuously the data. User is performing some kind of like yoga posture or exercise, and this data is being transferred to the server, and server has a recognition model which identifies, okay, the gesture, how the gesture is performed and which gesture is performed, and what is the correctness of this gesture. Then the feedback may be reported to the smartphone, and the user may look at the feedback that how accurately the posture was performed. Because in case of yoga, postures matter a lot. If you do not take the posture right angle and in a right way, then it may create some unnecessary consequences to your body. So it may happen, and that's why as early as you predict this, and you give some notification to the user that this posture may be corrected by this angle or something like that. So that means you may make some kind of decision regarding the user's posture. Another application, like I've been talking about already, like gesture recognition. So you have various gestures in your phone, and those gestures may be early classified in order to improve the user experience. When it comes to another application is fault detection. So let's say this is one home appliance, let's say washing machine, and in the washing machine you have several sensors deployed, because these days like every appliance is having like several sensors inside it. Although you are not able to get the raw data, they are making the prediction these days automatically. But in order to make that prediction, somewhere the sensors have been deployed, right? In order to get the information about the faults being occurred in this scenario, then those faults may also be detected as early as possible using the early classification. Because in this case, for example, if in the dryer clothes starts burning, then you don't have much time, right? You have just like few seconds of time. If within that time classification model is not able to make any decision, like it is going to break down your washing machine. So in the fault detection also, early classification is very helpful. In terms of like in automation vehicle, this is just an example I'm trying to show here, that a vehicle, this vehicle is trying to approach, is actually basically approaching a turn with a heavy fog. And due to this heavy fog, the turn light, the front light should turn on automatically. At the same point of time, the speed should also be slowed down automatically if there is no driver, right? There is no one driving the car. Or if the driver is there, then it may be alerted, the car may alert to the driver that slow it down or like turn on the lights. The turn on the lights is a kind of very common feature these days in all the cars. However, slowing down, it depends on whether the alert is coming to the driver or the car itself is taking the decision in order to slow down while predicting the fog and the turn. So with this actually application, we can think of that early classification is an important part. Right now, considering this early classification, there is like no freelance. So when you go for like making this early decision, you have to compromise with the accuracy. So what you got here on this slide, I'm just trying to give a general view of like length of the time series. So if you have like 100% time series, 100% could be like 120 numbers, 120 data points. It could be 200 data points. It could be 500 data points. Whatever it is, if it is like 100% time series, then you can achieve maximum accuracy. So the maximum accuracy could be again 90%. It could be like 80%. It depends on like application to application. But just by compromising a little bit of accuracy, you can make the decision early. So for example, if you come here, then by using just 70% of data, 70% of the length of the time series, my model can still make a decision with 90% of accuracy. Some accuracy is dropped here, maybe like 3-4%, but we were able to save the time. So obviously, in order to save the time, you have to compromise some accuracy, and that's why we call it like a trade-off between accuracy and earliness. Now, there are two different problems that I just mentioned in my the contents of the slide, that we will be talking about problem one. In the problem one, I will be talking about MTS with faulty data or faulty component. So you have this faulty, I'm just considering this application for human activity detection. So a person is equipped with different sensors, one on thigh and one on calf, wrist and chest. And these sensors are generating multivariate time series. So at one hand, you have a classification model that needs the complete multivariate time series. On the other hand, you have like incomplete time series. And you want to predict what activity user is performing. Now, in this case, this is actually just a multivariate time series. Now, in this case, you have like you may have two different issues. The one is like faulty data. So what if any of these sensors is actually generating some faulty data? So on the right hand side, if you see that I'm just representing there's some faulty data. So sensor is generating faulty data, then obviously it is going to affect the accuracy of the whole model. So one thing, if there is some sensor that you don't know and start generating that faulty data due to some reason, then can you still identify the activity using the multivariate time series having this faulty data? That's one part. The other part is like irrelevant component. So in especially this activity recognition task, not all the sensors are useful always for all the different activities. For example, if a person is standing, then the scarf sensor and the chest sensor, they may not be that useful like the wrist sensor or the thigh sensor. If a person is jumping, then the sensors more relevant are the calf, the sensor that is sitting on the calf and on the thigh. May not be that be useful the chest sensor. So the chest sensor, even if you have there, it will add up some accuracy, but it is not going to be very useful, because by using only the two different sensors, you will be able to predict what activity is going on, right? So just to showcase that, okay, that there exists some irrelevant component. When I say the irrelevant, it does not mean they are not relevant at all. They are relevant for some activity, but there are, let's say, 5 different activities, and in some activities, these sensors, these all sensors are not relevant. Some sensors may be relevant for this activity, some other sensors may be relevant for the other activity. Then, like, because when it comes to like computation, or when it comes to like earliness, then at that point of time, it is also matters that how many sensors you are being used at that point of time. Although the data is generated from all the different sensors, but you may try to minimize them to fewer while making the decision. And we developed a solution for this problem, and the paper has been published in IEEE Transaction on Mobile Computing in 2020. The another problem that I will be talking about is multivariate time series associated with an unseen class label. So you know what is unseen class label here. Unseen class label, I did not mean the class label that multivariate time series that has not been a part of training data set. I'm talking about an entire class label. So for example, you have a training data set which consists of like these 4 different classes. The 4 classes I am showing here by the different symbols. What happens if a new time series comes up which doesn't belong to any of these class label? So that means that model, the early classification model, has never trained on that class label. Still, we want to predict that class label. Is it possible? So the thing is that for early classification model, by default, it will predict it is actually a senior class label. So if it has been trained on 4 different class labels, in a new time series comes up, it will try to predict the class label out of one of these 4. But it will not be able to predict the class label, some new class label that it doesn't belong to any of these out 4. So that idea we have also explored or explored in the framework of early classification approach. And the work has been published in IEEE Transaction on industrial informatics. I think you may not be able to see that information. It is, I guess, it is hidden here. So the work has been accepted in 2020, and it is now published also in IEEE Transaction on industrial informatics. So now I would like to begin with the problem 1. I'll dig deeper in the problem 1. I'll take almost like 30 to 40 minutes to complete this problem and the solution and its result. And then later on, I'll switch to the next problem. There again, I'll take around like 15-20 minutes. And then I'll finish my talk with those. So as of now, you are feel free to interrupt me at any point of time if you have any queries. I would be happy to take your queries. So until now, if you have any query, please ask.
Students, you may ask for any queries if there are.
Okay, so I'm moving further now. I believe that you don't have query. Either you are not able to grasp whatever I said, or you understood everything very well. Okay, so now I take the motivation of the first problem, And the motivation that I already mentioned, that there are some components faulty data. So if there are components, and when I say the components, I'm actually referring to univariate time series. So the components means actually when it is a part of multivariate time series, that univariate time series, one univariate time series, I'm calling it as a component. In order to just to have a separation between the multivariate time series and the univariate time series. So instead of calling it like every time univariate time series, I will be calling it component. So we may have like faulty data components, and if they are there, if there are some sensors that are generating these faulty data components, then finally the accuracy will be poor for that model. Second issue is like there may be some irrelevant components. So if there are some irrelevant components that will increase the computation. That computation may be saved, and which is important in case of like resource constrained environment. Third is people did not use the correlation, because since whole multivariate time series is going to belong in one particular class, the correlation is very important there. So if you do not utilize that correlation, then the earliness will be very high, very low. So without the correlation, the earliness will be very low. So in our solution, we attempted to kind of like exploit this correlation. At the same point of time, we attempted to remove the irrelevant components, and while tackling the faulty components as well. So if there is any solution that can handle this MTF, when I say the MTF, that means MTF multivariate time series with faulty component. So there is an MTF, and if an LD classifier can handle this MTF, then it will be better for the faulty environments, and it will take lesser resources compared to the one which was considering all the components irrespective of their relevance. Here actually I'm defining the problem in mathematical form. So you have a data set, and the data set is, let's say, D, training data set. We have multivariate time series, and each multivariate time series I'm using the notation capital C with the superscript J and its class label. And there are total capital N number of training instances. So that means there are total capital N number of multivariate time series. And each of this multivariate time series I'm calling as an instance, and has like N components. So that means there are N different univariate time series in one particular multivariate time series. So a small n I'm taking as like the number of sensors we are that are creating multivariate time series. Each component is completed. I mean complete in the sense that it is consisting m data points. So m is the actually complete. So when I say the complete time series, that means I'm talking about total m number of data points, capital M. And there are total small l number of class labels. So we have total L class labels, you can say that, in the data set. Now, given this setup, what is the problem here now? So the problem is we want to predict the class level, let's say LP, and so given a multivariate time series MTF, which does not belong to any training data set, that means it is a testing time series. We want to give that what is this F, and F is actually the number of data points starting from 0 to capital M. So it will lies between 0 to M, and lesser the value of F, the better the algorithm, because we want to classify as early as possible. So F starting from 0, it may reach up to M. If it is reaching to M, that means we are not getting any earliness. And if it is reaching to like F equal to some 50% or something, that means we are getting 50% earliness in there. The assumptions are quite clear here. Training data set contains complete labeled multivariate time series, and second is training data set does not have any faulty component, because it is going to be useful for learning what is faulty components. So there should not be any faulty component already in the training data set. Otherwise, model will not learn well on the training data set. So before I go to the solution, I would like to define one term, that is MRL, minimum required length. And it is actually the number of data points that are of any particular component that are required to provide a desired level of accuracy alpha. So if you look at this picture, for example, this is a time series, and when it gets completed, you get some accuracy on it. And this is the maximum accuracy you could achieve. It could be like 80%, it could be 70%, or whatever it is. It does not always have to be like 100%. But whatever the accuracy that you get with the complete time series with like capital M number of data points, this like in complete time series, you get one accuracy. And if this accuracy is greater than or equal with some alpha factor of the actual accuracy with complete time series. So this alpha mostly varies from 0 to 1. So if you have alpha equal to 1, that means you are trying to have like both accuracy same. And if you are targeting for both accuracy same, then it is very unlikely to get an MRL, because there will not be any MRL, because you are targeting for the 100% accuracy. That means relatively you are targeting like 100% accuracy. But when you say the alpha equal to, let's say, 0.9, that means you are able to make you want to make a compromise of, let's say, 10%. And if you make a compromise of 10%, that means you can achieve some MRL now, right? And you have to learn this, right? The model has to learn this, that what should be this MRL for different class level, for different components, having this alpha given. So now the overview of the solution, if you look at this picture. So overview of the solution, we proposed like fault tolerant early classification approach. It consists of two different phases. One is testing phase, other one is training phase and testing phase, and which are very classical in case of classification algorithm. There are always like one training phase and testing phase. It depends on what you do in the training phase. It varies from approach to approach. So in the training phase, I have like 4 different steps. The first step, because we have given the data set which consists of several irrelevant component, may contain several irrelevant component. So first we attempt to obtain relevant sub-data sets. When I say the sub-data set, that means the data set with fewer components. So if there are like capital small n number of components, then you may have like n minus 2 components in one sub-data set, n minus 3 in one sub-data set, and something like that. So you may have several sub-data sets such, right? So I just wanted to find out what are the relevant sub-data set first. Then in the next step, I will estimate the minimum required length, that means the MRL for each of those sub-data sets. And then again, I try to prune some of those relevant sub-data set, because so all this relevant sub-data set that we found in the first step may not be useful again, or they are useful, but they are not actually giving some more accuracy or some earliness. They are losing somewhere. If they are still losing somewhere, then we will prune them out. And finally, we will estimate the MRLs for the rest of the relevant sub-data sets. Those MRLs will be used in in the testing phase during the prediction of class level. Another step that we have in testing phase is estimate error threshold in order to identify the faulty components. So we will estimate the error threshold corresponding to each of the component, and the estimated threshold will be utilized in identifying the faulty components during the testing phase. So I'll go to each of the step in detail. So the first step, obtaining relevant sub-data sets. So in order to obtain the relevant sub-data set, what we did, we started actually we computed a relevancy score of each component. So we have like a small n number of components, and we computed the relevancy score of each component, how relevant the component is. And in order to do that, what we did, we take this subtraction, and this subtraction says the accuracy on the whole data set, that means the D, which consists of all the components, and accuracy on the data set which does not contain ith component. So if you have like the data set with accuracy with all components and then accuracy without one particular component, then that will give the relevance of that particular component that we have removed from the data set. So this difference will give us actually the relevancy score here for that component. And this relevancy score will be used later on in next few steps. So given this relevancy score, we will be actually arranging these component in some order, like some high relevancy order first, and then the lower, like keep decreasing the relevancy scores, and then we'll arrange the multivariate time series in that way. Now the example here is for obtaining the sub-data sets are like the one that I'm showing here down in the picture. you have, let's say, 4 different components, 1, 2, 3, 4. That means multivariate time series consists of like 4 dimensions and 4 components. And out of these 4 components, you have like several possibilities. You have like, let's say, 16 possibility here, making different pairs of components. And you don't know like which of them are going to be going to give the same accuracy or not, right? So that's why you have to test them all out, all of these sub data sets, in order to find out the relevant one. So if you look at the right hand side, then we have some red node, and these red nodes are actually the ones that we are going to prune out, that they are actually irrelevant. Irrelevant because if you look at this arrow, and this is saying like this accuracy of on this data set, the data set which having this like component 3, 1, 2, 3, 3 components, right? These 3 components, it is giving us the accuracy which is lesser than the compromised accuracy even. So that the accuracy with the complete one, and we multiply with this alpha factor. And even if the accuracy is coming less than this, that means this particular subset is not going to be useful, right? It is not providing the desired level of accuracy, right? We are making the compromise on the accuracy, but still we are not able to achieve any earliness, and we are not able to achieve the desired level of accuracy by using these 3 different components. So if you drop these 3 components, immediately its descendants will be dropped. So 1, 3 will be dropped, 1, 4 will be dropped, 3, 4 will be dropped. So all of its like subsets will be dropped. So after dropping these, we are able to manage only just few of these relevant subdata sets. So the white ones are actually the relevant ones for us, and we will be using them in the next step. So given those subdata sets as relevant subdata sets, for each of this subdata set, let's say as we estimate the class-wise MRL and class-wise MRL for individual component, and then we estimate the class-wise MRLs for this whole data set, combining all the different components. Example here, I'm just showing for the MRL in order to understand the MRL a little better, because the MRL is like the lesser size of or the fewer data points of any particular time series. So for example, let's say in the data set, we have 4 different class labels, and we have got like 4 different MRLs. So M is actually the maximum length. This is showing actually the timeline of the time series. So you have here 4 different class labels. And for instance, if you take this like L3, so for predicting the L3, you need to have at least F3 data points in the time series, right? So what is the meaning of this? The meaning, the actual or the ground meaning for this is that with this F3 data points, if a classification model makes a decision about L3, it predicts, let's say this is L3, the given time series belongs to L3, then you can rely its decision. If it predicts, let's say L2, given this F3 data points only, then that decision is not reliable, because we identified during the training this for L2, in order to predict the L2, you need to have at least 4 F2 data points. So with F3 data points, you can predict all the previous ones. You can predict L3, you can predict L1, L4. So the classification model, given this, because the classification model doesn't know that which class it is going to predict, right? Based on the training, it will predict some class level, and that class level will be out of these 4. It could be L2. If it is L2 and we have used only the F3 data points, that means the decision is not reliable, because to predict a L2, you need to have at least F4 data points. So this is what the class-wise MRL means. So we have, respective to each class, we have one particular MRL, and that MRL ensures that before that, all the class level can be predicted reliably. But after this, actually, if you predict any class level, you cannot rely on the system. You have to wait for more data points, because the data points of like F3 data points are not sufficient to make decision on the L2, right? You have to wait for more data points. And what is happening in the underlying classifier, that given this like data set, you have all the capital N number of training instances. The training classifier, the classifier would be trained on the L3, and you have to wait in all the time series in the training set would be using up to F3 data points, not M. So during the training also. So likewise, you can think of, there are several classifiers sitting in the background. You have like, if you have, let's say, a small L class label, right? And then you have So for each class level, you have one classifier, one thing. So you have got like L classifier if you have L class level units. The second part, for each of that class level, you have like capital N component. So for each component, you have again a classifier. So you got like L into capital N number of classifiers sitting back in your system, and one of them is being called based on the number of data points that you got in the testing time series. So with this, actually, I can just give a little detail on like how to compute the class-wise MR on individual component and then for multivariate time series component. So on individual component, I'll just go quickly through this slide because it contains a few mathematical notations. But like you first apply k-means clustering on the data set, you get like prior probability and members of probability for each instance. Then you apply a KNN classifier on the S in order to get the posterior probability. And using these three quantity, we compute an accuracy. And that accuracy is also having this factor alpha in order to show that what is the desired level of accuracy, and that will be actually work as a dividend in order to reduce this accuracy or suppress this accuracy between 0 to 1. So you have given like this membership probability, and then you have a posterior probability. And using this formula, you compute. We kind of formulated this formula to obtain a relative accuracy. Once the relative accuracy is obtained, then we compute the utility. So whether the given time series and is it useful enough or not. So the earliness here is actually we compute it as the number of data points we have saved. So for M is the number of maximum data points we have, F is the number of data points that are being used currently, and we take the percentage of this difference, right? So and this is just like harmonic mean. So you have this harmonic mean of corresponding to each instance. When I say the each instance, that I mean to say like exactly one univariate time series. So for each of this instance, you compute a MRL, and this MRL is the one which is like which is having like maximum utility. So we compute the maximum utility for each of the instance, and we got one MRL because we are getting this like arguments F. So the maximum MRL we get, right, the maximum utility we get, and we take this like the size of the value of F and assign it to MRL. We compute it for all the instances. We have, let's say, a capital in total, we have like capital N number of instances, but however, they are distributed across different class levels. So for, let's say, NQ class, NQ is representing actually the total number of instances belonging to LQ class level. So because we have like several class level across all the class levels, we take all the instances of one class levels and we take the average of those MRLs in order to give one particular number or one particular MRL for that whole class, right? After computing this MRL for each of the class level, for each of the component, we use a method that is called a class forwarding method in order to extract the correlation. Because when it comes to use all the multivariate time series all together in a setup, then you need to have like a correlation among them, and that correlation somewhere has to be extracted. So you have now, excuse me. So you have this MTS, right, with all the components, and let's say there are S relevant components. Then what is happening here? That we know that all HF are actually already prepared in the last slide, because we have like all the different MRL, and we have a classifier corresponding to those MRLs for each of the individual component. Now I just wanted to utilize the correlation among all of them, I mean all the component, so that we can directly give one MRL for this like whole multivariate time series. So one multivariate time series, we will have like one MRL. So what we do, we take out actually the MRL of the first component, and here the components are arranged actually based on the relevancy order. It is not because we have to make some arrangement, and then you can forward the class. So this C1 is the highest relevant component, and the relevancy we have computed before. So it utilizes the number of F data points initially that has been kind of like obtained in the previous slide. and the classifier will wait for those f number of data points in the component C1 and will try to predict its class level. So if this class level L1 is the predicted one, and if it is going to the same with like the ground truth, then we consider this MRL in the set. And likewise, what happens so that we keep doing it for all the different components, and we get the f value for all the different components here. In this set, finally, we compute the maximum of those values, and we say that this is the MRL for that particular instance. So for each multivariate time series, we get now one MRL using this method. And this method is actually, because you see that the MRL here is utilized from the previous predicted class level. So the class forwarding, we call it like class forwarding method, and through this class forwarding, and this is the new idea as of now, nobody has utilized this idea before, in order to extract the correlation. So the correlation here is being used in terms of by class forwarding. So the predicted class level from a previous component will be transferred to the next component, and it will help the classifier somewhere, right? Because all these components are going to be in the same class level, that's why. So finally, we get actually one MRL, and this MRL is being used as one MRL for this whole multivariate time series. We do it for all the instances. Finally, we do the average over the classes also, right? So for each class level, we get one component, one MRL. So now see this image, right? For a particular whole multivariate time series data set. For all the relevant sub data set, for each of that one relevant data set, we have let's say capital N number of instances. So this function, the one that I'm showing here on the slide, will go through all the different N instances. Now for each of that instances that there are, let's say, a small L number of classes. So some of the instances come in class L1, then L2, and something like that. So you have all the different N instances divided into different L class levels, and for each class level you have one MRL now. So in total you have now L MRL only. You don't have individual component MRL. Individual component MRL has been used here as a class forwarding method. So finally we have small L, and L is actually the number of class level we have. So we have only the set of L MRLs corresponding to each of the class 5 level. Now once we have computed, now we are coming to the third step in the training phase. In the third step, we are trying to prune the relevant sub data set. So first we got the relevant data set, right? Then we compute the class wise MRL, and now we are going to utilize the class wise MRL in order to prune out further some nodes. So the green ones actually are removed further, although they all were actually relevant sub data set, but they are still lacking some I would say the earliness. So if we use this formula in order to remove out further nodes. So the green ones are actually removed based on the accuracy, because all these nodes, all the white ones node, they are giving the right amount of accuracy, the desired level of accuracy, but they are not providing sufficient earliness. So we may still remove them. So we remove those prune node, and only the white ones are left further and for the further processing. On the next step, this is the last step of the training phase, and in this step you have to identify the error threshold. So in order to estimate the error threshold, we have used the ARIMA models, because the ARIMA model was quite perfect in this case, because we have the maximum permissible error. I just wanted to have corresponding to each component. So whenever a new component, or actually new univariate time series coming up from one particular sensor or one particular component, you have to identify whether that is within the maximum permissible error or not. So this maximum permissible error, we have used ARIMA model on each of the instance in the training data set, and attempted to identify the maximum, the difference between the actual value and the predicted value. And whatever is the maximum, if any point of time, if in a new time series it is going above this maximum threshold, then that component may be identified as a faulty component.